All right, in this video we're going to talk about joint and marginal probabilities. Simply stated, joint probabilities refer to the intersection, the probability for the intersection of several events, and marginal probabilities refer to the probability for just a single event. And hopefully these are all concepts that you're all fairly familiar with already. So let's take a look at an example. Here we have a professor who has a class that has joint enrollments from undergraduates and graduate students. So the class is full of graduate and undergraduate students, and the professor wants to know, is there any relationship between a student's enrollment status, whether they're undergrad or graduate, and whether they get an A? So is there a relationship between being an undergrad or a grad and getting an A? Maybe the professor is considering restricting the class only to graduate students, but needs to find justification for doing so, saying, well, maybe there's a relationship between how well they do in terms of grading and their enrollment status. So let's take a look at this and how we might do this. First of all, I want to point out we have this list of, there's 100 students in the class. We have the list of all the students. And I've got various calculations done which are counting the attributes of those students. So what we can see is there's 100 students. We've counted all the cells that include some text, and then I've subtracted one for my headings. So there's 100 students, there's 40 A's, 40 B's, 20 C's, total of 56 graduate students and 44 undergrads. Here's the key in looking at joint and marginal probabilities. So you can see already, okay, we've got these two statuses, their grade and their enrollment status, and often with joint and marginal probability problems, you'll see, often they might just be referred to as joint probability problems, you'll see a table like this, where we've got these two statuses, and these are all the possible outcomes, right? We've got 26 graduate students that have received A's. You can see the equation I used up here. I'm doing a count only if they got an A and their status is G for graduate student. Same thing over here, counting if they have a B and their status is graduate, counting here if they got a C and their status is graduate. Same thing down here under undergrads, we're counting if they get an A and a U. And so we see that there's 26 graduate students who received an A and 14 undergraduate students who received an A. So right off the bat, we're like, that seems like a lot more graduates receiving A's, but there are more graduate students in the class. So how are we going to prove that there's a difference here? I mean, aside from sort of eyeballing it and seeing like, well, the ratio up here looks a little bit bigger than the ratio down here, we can do a test. So we have to test for independence. If these are independent events, there will be no relationship between the two of them. But if they're dependent events, there will be a relationship, so we can test for independence. I'm just going to write here on my Excel document. It's not going to look as nice, but we won't have to leave the page. Probability of A intersect B. What's my A and B here? Well, let's define these. I'm going to define A as that they're a graduate student, grad student. Boy, this is messier writing here. And B is going to be received an A. Okay, it looks a little bit junky, but bear with me. So if these are independent events, then the intersection of A and B will be equal to the intersection, it's equal to the product of A and B. So this is a question mark. Are these equal? Well, let's see. Intersection of A and B here is this. That is, they're a graduate and they earned an A. So this is going to be also known as 26% of the class. And over here, probability of being a graduate student, I should say, that's probability of event A, being a graduate student, is 56 out of 100, so that is 56%. And B is received an A. There were 40 A's out of the class, so 56 times 40, 56% times 46 times 40%. I'll work this out eventually. 0.56 times 0.4 is equal to 0.224, otherwise known as 22.4%. Does 22.4% equal 26%? No, it does not. So these are not independent events. Okay, that tells us that there is a relationship between being a grad student and earning an A. It doesn't tell us the direction of the relationship, but we can figure that out, actually. In fact, we can do one better than that. We can go ahead and figure out what that relationship is. So to determine the relationship between being a grad student and earning an A, or being an undergraduate and earning an A, I might start by creating a decision tree. I'm a big fan of decision trees. You're going to see me use a lot of decision trees throughout these videos. So a decision tree is a great way to represent joint probabilities. It shows basically divergence of events and the way they have a relationship with each other. So let's start by saying we have two paths here. We can either be a graduate or an undergraduate. Hopefully that makes sense to everybody. And then if you are a graduate student, you can either earn an A, a B, or a C. And if you're an undergraduate, you can earn an A, a B, or a C. Nobody failed this class. It's nice. All right, now we know that there are 56 graduates and 44 undergraduates, so we'll call this 0.56. I'm back to using decimals now, bear with me. I just don't like writing out the percentages and the whole whatever. And we know of the graduates, it's an interesting thing here. We don't actually know the percentage of graduates who are going to earn an A yet. We're going to figure that out. But we do know that of all the students, 26 out of 100 were graduates and earned an A. And 22 were graduates and earned a B. And 8 were graduates and earned a C. So this is G A, G B, and G C. Down here we know that 14 undergrads earned an A, 18 undergrads earned a B, and 12 undergrads earned a C. So now how do we figure out what percentage of graduates, what the likelihood of a graduate earning an A is? Hopefully, many of you are now saying to yourselves, this is conditional probability. If we've defined a graduate, then this is just going to be, this is the intersection of being a graduate and earning an A. Remember, conditional probability, the condition here is that they're a graduate, so we're saying probability of A given graduate, that's equal to A intersection, not B. A intersection G over probability of G. So what's this going to be equal to? Well, this is going to be equal to the intersection, which is 0.26, over G, which is 0.56. So it's going to be 0.26 over 0.56. And the probability, and actually let's calculate that out. I'll just use the same cell I was using before. Equals 0.26 divided by 0.56. That's going to be 0.464 approximately. That's A given G. Let's figure out the same probability for undergrads. If you're an undergrad, what's the chance that you're going to earn an A? So again, this is going to be, now it's going to be A given U. That's going to be equal to probability, the intersection A and U over probability of U. And we know the probability of U is 0.44. And the probability of the intersection is 0.14. You can tell already this is going to be a considerably lower probability, 0.14 divided by 0.44. So if you're a graduate student, chance you're going to earn an A is almost 50%. It's 0.464. 46.4%. If you're an undergraduate, the probability that you're going to earn an A is just barely over 30%, not even a third of a chance. So 0.138. So can we say graduates are performing better in this class? Well, at least in terms of earning A's, they are. Yeah. And actually, this could be borne out if we calculated probability of earning C's as well. You'd see that graduates do, on the whole, considerably better in this class. So does the professor have a case for maybe restricting this class to just graduate students? Yeah, looks like it. So for our next example in joint and marginal probabilities, let's go back to the whiteboard. In this scenario, we're running a stand that sells milkshakes. And we want to know, is there a relationship between the ice cream flavor that our customers order in their milkshakes and the size of the milkshake that they tend to order? We've got 3 different flavors. We've got chocolate, vanilla, and strawberry that I've abbreviated here. And we want to know, based on our sampling data, is there a relationship? Do people who tend to prefer one flavor tend to order smaller or larger cups? And we've got this table here. And we can use this table to determine the relationship between, if there is a relationship between flavors and cup size. So I'm actually going to move this over just a little bit, because the first thing that I like to do when I see a table like this is I want to get the totals. And you'll see why in a moment. So I'm going to use a red color for totals here. First of all, I want to know how many people are ordering chocolates. I don't know what my sample size is. It doesn't matter. These are all percentages here. So if I want to know what percentage of people are ordering chocolates, I have to add up the people who are ordering small chocolates, medium chocolates, and large chocolates. And these are all percentages based on my entire sample. So if I add up 9.1 plus 11.2, that's 20.3 plus 14.7. This is 35%. That's not the color I wanted. %. If I do the same thing with vanilla, 18, 19, and 13, I get 50%. And now I can just say, well, add these 3 together. This has got to equal 15%. I'm going to do the same thing to figure out the percentage of customers that are ordering small cups. So if I add these 3 together, I get 32.8%, 34.7%, and 32.5%. All right, now what do I do with this? Well, let's do a decision tree. This is a joint probability problem, so let's start with a decision tree. Now, since we want to know, is there a relationship between, do people who prefer certain flavors tend to order larger or smaller cup sizes? Let's start with the flavors, because that's what we want to start with flavors, because we want to know the relationship of cup size to flavor. So I've got 3 branches here. We'll see if I give myself enough room. I have to make kind of an ugly decision tree here. We've got chocolate, vanilla, and strawberry. It's going to get dicey. And then we've got small, medium, large, small, medium, and large. Down here, small, medium. No good. I'm going to need more room than that. Small, medium, and large for strawberry. Okay, we know that of all of our customers, 35% order chocolate, 50% order vanilla, and 15% order strawberry. We know that. That was given to us. We got that by adding up the totals here. We also know that of those who order chocolate, the intersection between chocolate and small is going to be 9.1. That's chocolate and small. 11.2 for chocolate medium, and 14.7 for chocolate and large. We can use the same principle to figure out that it's 18 for vanilla and small, 19 for vanilla and medium, and 13 for vanilla and large. 5.7, 4.5, and 4.8 for strawberry. So where do we go from here? All right, so what we've got is we've got these, the probabilities for each of the flavors. We've got given those flavors, we've got the probabilities for each of the cup sizes. Well, that's interesting. This is essentially what, this is conditional probability. I hope you all can see that. Given chocolate, given that chocolate is our flavor, this is the breakdown. So what we really want to know is, let's start off by saying, well, what we really want to know is what's the probability of size given flavor, right? And that's going to be the intersection of size and flavor over probability of flavor. Now, this is not good statistics. This is not good probability. I hope some of you are thinking that to yourselves. These are not real events. You can't say an event is size. You would say an event is size large, and the flavor is chocolate. But let's actually do that. Let's say A is large and B is chocolate. Those are real events. So we actually really could do this equation here. Let's figure this out. So now we want to know, actually, let's put it down here. Probability of getting a large size, given that the flavor is chocolate, is going to be equal to P A and B over probability of B, which is going to be equal to this right here, 14.7. That's the intersection over 35. And what is that? That's 42%. Huh. Now, if I'm filling out my decision tree, I can put that right here. And I can do the same thing throughout all the branches of my decision tree. These are the conditional probabilities. This second branching of the tree is really going to be, and to make sure that this makes sense, think about this. 35 times 42 is going to be equal to 0.147. These could all be converted to percentages, which is what we were using originally. It's the exact same thing. This works. So let's continue working through this thing and filling out the tree. 9.1 out of 35 is going to be equal to 26%, and 11.2 out of 35 is going to be equal to 32%. You're just going to have to bear with me. Notice that this should all add up to 100, and these two are 74 plus 26 is 100. And I'm going to clean this up a little bit. Get our branching looking like it did for chocolate out here for vanilla. So I think it's a little bit more efficient. Same exact concept here. We're figuring out the conditional probability. So we're saying if the flavor is vanilla, what is the percentage chance that it's small? Well, that's going to be 18 over 50, 36. 19 over 50 is 38. And 13 over 50 is 26. Again, these add up to 100. 36 plus 38 is 74, plus 26 is 100. And now we can actually, I could keep going with strawberry, but I'm not going to because you don't all need to see that. But notice this. Are we prepared to make a statement about, do people who prefer certain flavors tend to order larger or smaller sizes? Well, yeah, we can say that. I mean, now you can sort of forget about everything over here and just say, someone who orders chocolate, 42% of them are going to order a large, and 26% of them are going to order a small. But among the people who order vanillas, 26% of them are going to order larges, and 36% of them are going to order smalls. So, yeah, people who order chocolate tend to order larger sizes. They tend to go larger more frequently than people who order vanilla, and smaller less frequently than people who order vanilla. So, yeah, tend to make a bigger order. Now, I made all of this up, of course, so, take it with a gigantic grain of salt. Let's see if I can. I don't think I can fit any more on this page, so I want to point out one more thing. And that is, what if you had made this decision tree in the exact opposite way? What if, and here I've got all this room, it's going to be glorious. What if I had made my decision tree like this, and I had said small, medium, large? What would that have given me? Think about that for a moment. We're going to have branching again, but now it's going to go into, we'll say, chocolate, vanilla, and strawberry. Chocolate, vanilla, strawberry, chocolate, vanilla, and strawberry. I'm not going to fill out this whole tree, but we can go back here and we can get, okay, we say there were 32%, 32.8% smalls, 34.7% mediums, and 32.5% larges. So we'll fill that in. 32.8, 34.7, and 32.5. And I'm just going to do this for the smalls. We can say, going back here, 9.1 of the smalls were chocolate, 18 were vanilla, and 5.7 were strawberry. So we go 9.1, 18, and what did I say, 5.7 were strawberry. Now, you can do this. You can start adding these. Notice that these will add up to 32.8. That's 27.1. 27.8 plus 5 is 32.8. We could figure out, for instance, what this number is here. This of the people who order a small cup, what percentage of them order chocolate by just dividing 9.1 by 32.8. This right here is going to be 9.1 divided by 32.8. But what does that really tell us? Well, what it tells us is, it tells us the probability of someone ordering chocolate given that they've ordered a small cup. It's not what we were looking for when we asked this question. We asked the question, do people who prefer certain flavors tend to have different cup sizes that they order? This tells us, do people who order a certain cup size tend to prefer different flavors? It's a subtle distinction, but it's important as we're doing our analysis.